Hi, I am Dr. David Horn, and I'm here to talk to you about flat physics in the laboratory, observations of vortex interactions in a flowing 2D soap film on behalf of myself and my student Lily Sheng, who ultimately became my graduate research assistant here at Gannon University. So, our first question is why flat physics? Why are we studying this at all? And this is a project that's been a long time in the making. As an undergraduate student myself, I embarked on this project about 20 years ago, and I've been an astronomer since, and then came to Gannon University, where I was looking for a project that I could resurrect, which I've always wanted to get back to, which could actually engage students from different backgrounds. Gannon does not have a physics major or minor, and then I decided I would appeal to engineers. We have an excellent engineering program, chemists, we have biologists, and we have software engineering. And I really wanted to involve students in my particular field of research. So I returned to the flat physics. We have a lot of good 3D printing and a lot of people who are very adept at CAD design, and it really lent them to this particular project. So again, why 2D films? Well, in 3D, turbulence tends to undergo forward cascades in things like streams, the ocean, these kinds of systems, and the energy is translated to smaller and smaller scales. In a 2D turbulent system, the vortices go towards reverse cascades, meaning they get larger and larger. The effect was actually predicted quite a while back in 1967 and wasn't observed till the 1980s, and it applies to a lot of different disciplines. As you can see here, my high school intern, Bryce King, actually has his finger in the film as an obstruction, and my student involvement is being catalogued in a paper to the physics teacher, which is currently under review. So in terms of applications of our 2D turbulence system, we really want to look at vortex streets and flow patterns around objects, and we want to better constrain this as a 2D mathematical model. So we're really looking at situations in nature, such as, say, stratified flow. And I realize that the atmosphere is a three-dimensional system, but any one particular layer in the atmosphere is relatively thin compared to its thickness. And in some ways, you can see this sort of two-dimensional flow pattern actually formed in the atmosphere of planets. So here's a typical result. On the left-hand side, in black and white, we have our classic wind tunnel. And on the right-hand side, in the green, we have our 2D soap film. This has been tipped on its side 90 degrees and is actually flowing under gravity. It was turned on its side so that it could be compared nicely with the classical wind tunnel experiment on the left. But you can clearly see in our experimental system how the flow is going from a laminar state into a turbulent state as it passes around the object that's obstructing the flow. I did not invent the method that we actually used. I actually put together a machine originally, as I said, a long time ago, based on the methods of Rutgers and Wu from 1997. I have actually made quite a few innovations, though, as time has gone on. Our injector is significantly improved with the lines running through the nozzle, and it is machined as such. We also have improvements in high resolution imaging with improved frame rate for low cost. Our film thickness sits at about 2 to 6 microns, and that's based on the interference patterns that we can actually see, but we do have a laser upgrade planned, so we will actually determine our film thickness through laser reflection. Our flow rates are on the order of about half a meter a second to about 5 meters per second. Here's what we call our Generation 2 Mark II soap machine. As you can see, it got a little out of hand and we've had to take the ceiling apart to accommodate it. It has a height of about 1.6 meters, giving us a test zone about 0.8 meters across. We can also be made to be smaller and constrain the flow should we need to. It has a capacity of about 28 liters or 7.5 gallons, giving us a duration of many hours. We also have a collecting tank at the foot of the system, which recycles the soap film back into the tank. There's a heater that gives us an optimum temperature of about 40 Celsius, and we get images at about 1080p at 60 frames per second, upgraded to 1080p at 240 frames per second. And we are hoping to get up to 422 frames a second at 4K with a proposed upgrade. Here's how we make a film. Here's Bryce touching these two lines together. As you can see, the flowing soap going down one line and then extruding out a soap film. As you can see, there's a lot of reflection there. It is flowing and you can just about see it, but that reflection is a significant problem. And so we actually look at this under a filter, 546.1 nanometer filter, to bring out the interference patterns. That helps us determine a thickness, but also helps us see detail within the film. In terms of obstructions, we have 3D, FDM, and SLS printed shapes. We have an excellent 3D printing facility here at Gannon and students who know how to operate it. Our wakes are induced as the fluid flows around the obstruction, and we can design these obstructions to give us specific wake patterns. For reference, the ellipse at the bottom of the screen there is about 90 millimeters across. And here's Lily putting a shape crudely into the film. The students do enjoy putting shapes into the film, and sometimes these have very scientific results. Other times they just wanted to see what happened. Either way, a lot of these results can be seen on YouTube and TikTok, platforms that they enjoy posting their results to. And here's a typical result. Here's a flat plate put into our flow, and you can actually see the effects of the turbulent, chaotic flow behind the plate as it's blocked. Here's a number of results from our system. As you can see, there's that 90 millimeter ellipse on panel E and a half ellipse over on panel H of the same dimension. You can see in a lot of cases how the fluid flows around the object, panel G specifically showing the kind of distortion that we can see in the film and the vortices generated by that object. Panel A here shows a typical laminar flow without an obstruction introduced to the system. So here's where I come in. I actually do the software analysis here, and I have an automated system written in IDL, the interactive data language, to look at the pixel values in a grayscale system and actually count up the different colors, essentially the intensity of the pixels, and then actually track the structures and track the vortices from frame to frame, which, as you can imagine, at 240 frames per second creates a relatively large data set. Recently, an innovation I'm attempting to make is that instead of looking at the system in grayscale, is to decompose each channel into a red, green, and blue, and then track the different features through the different channels. By doing this, we can actually eliminate some reflection and some artifacts that we got in the previous case. As you can imagine, we're now dealing with 3 data sets as before than we were before, and still at 240 frames a second, which over even a 5-minute observation period makes for a very big data set. In terms of our conclusions, we feel that we have validated the use of our soap film system for scientific testing, and we're using a lot of the off-the-shelf technology that we can find. So this is a relatively low-cost experiment that lends itself to student use and to possible expansion at other facilities should anyone else be interested in asking us how to build this. We are building large data sets. We're essentially building an encyclopedia of data for various different sizes and shapes. And I am now seeking programmers to help me with AI and predictive algorithms to look at the path and size of our fluid features. Further advancements, we want to look at film thickness determination through laser scattering, also seeding the film to look at the speed of the film, development of mathematical models, of course, which is our mandate, and rotating the shape, something we've already experimented with. But here we will do a little bit more work on that before we release it. But we're looking at vortices shedding from rotating asymmetric shapes. And of course, variable geometry obstructions like the cylinder with little drag flaps that could actually move. And finally, here's some of my references, mostly from the original project that have expanded a little. And we have some shameless self-promotions for our TikTok and YouTube channels.